I work for Cloudera, and I actually work on data storage projects. So that includes Avro. I'm actually an Avro committer, Parquet PMC member as well, and the Kite project, which is pretty much what this talk is about, so I'm not going to ruin things later by going too far into it. Those are our three HDFS-based storage projects, and I work on those. So I want to start things off with a very quick show of hands, because it's going to really matter. Who all has seen the movie Fear and Loathing in Las Vegas? Not as many hands as I was hoping for, because I'm going to heavily reference this movie. So someone pull it up on Netflix, and we'll have to do this in a couple hours. Okay, so, sorry, that's the joke. I'll just explain what's going on here. In this movie, it's about Hunter S. Thompson basically going on a very long bender in Las Vegas. And he, at one point, takes some heavy drugs and wakes up a few days later in his hotel room. And at this point, he has a giant dinosaur tail and a tape recorder duct taped to his chest. And he goes and finds out what the heck just happened in the last couple of days. And I think being in the Hadoop community is pretty much the same thing. We all went to a NoSQL party, and we woke up 5 minutes later, and we're like, or sorry, 5 years later, and we're like, did we build a database? What the heck happened? And you know what? We have all of these artifacts of our crazy, wonderful experience that I'm going to call Dinosaur Tails. So we've got a few Dinosaur Tails, which are just the quirky, who knew we were building a database at the time, artifacts of the amazing experience that we've been through. The last presenter had 3 bubbles. There was 1990, and then all of a sudden, 2008, Hadoop's the main thing. And we built a whole lot of stuff on Hadoop, and then thought, maybe we could have done that better. So, here's some Dinosaur Tails that I think are the rough edges of Hadoop today. So, some tools work with tables, right? We threw SQL out the door and then realized, hey, we do the same thing all the time. Maybe we should be able to aggregate. And so we built tools like Hive, Impala, Presto, all of these things at the table level. And we did that because SQL hides all of those underlying storage details from it. But we still had, checking our tape recorder, what the heck happened here? We had tables come later. And we had MR, which was based on this idea that I can commit data to a data set by moving a single directory. So we just still have both. And in fact, this is kind of a huge pain if you're trying to write a Spark job or an MR job or anything that accesses data in HDFS. Table formats are actually re-implemented everywhere whenever you want to say, okay, I need to go to this directory, some subdirectory within that, and pull up just the data that I need for this job. So jobs have trouble reading, and they also commonly just write data into these folders with very little regard for database semantics, which is what other products are trying to deliver. All right, second dinosaur tail. If you can dream of a file format, Hadoop supports it. And someone's probably storing a petabyte of data in that file format, right? So we've got my favorite, which is delimited text files. We said, yeah, we can just do CSV, right? And then thought, oh no, that was a bad idea, because CSV isn't splittable. It doesn't have all of these properties that we actually need to be working with data in Hadoop. Not only that, it's not compressed. There's really no way to compress it. It's a terrible idea. But unstructured data was part of the appeal of Hadoop in general, right? We wanted to be able to swap in data formats and swap out data formats really easily, and we just used that a little too much, right? So today, we have all of these data formats where we probably shouldn't. And delimited text is a really great example of it, because we have databases or SQL layers that are based on this delimited text standard when they shouldn't be. We have these lurking application problems. All right. Up next, we're back to how we write data in HDFS. We have this de facto table format where I create a directory for some level of partitioning in the table. And I actually do this completely by hand, right? How many databases do you tell which partition you actually want to access? So we've mixed all of this metadata in, and we've done it in such a way that you have to, with every Hive query or Impala query, say, I want to go to this exact directory, just like you do with MR, just not working with paths and file systems. What we intended was this to be a very simple system, right? Well, we need to put data in Hadoop in such a way that we can ignore most of it most of the time. Partitioning does that. It provides a coarse index into our data and allows us to scale beyond a single directory. But then we have all of these problems. We have to have an elaborate locking scheme because our simple table format says any valid file in that folder is part of the data set. So if I want to take 4 small files, turn them into one large file, I all of a sudden have to lock and say, no one else read for a while because there's going to be a period of time where I've deleted 4 files and have not yet added the other file to replace it. And if we do that locking, then queries are incredibly slow. So most of the time we just deal with the fact that, well, if you query that table, you might get a sort of incorrect answer, but it's probably only for a millisecond. All right. The last dinosaur tail here woke up completely, clueless, and the tape recorder had actually gone out. So schemas are missing key features. Nullability for one. Why can't you say in Hive, this column is never null, right? It's an important column. It's, say, employee salary. We don't want that to ever just be missing, right? I have no idea why we're missing these features, but we're missing things like dates and times, and for anyone in the financial industry, say, decimals or, fixed precision things. Like, we've built a serious amount of database with some very substantial flaws. So, consequently, what we end up with is this situation where building applications on top of Hadoop is extremely hard. Now, there are a number of overarching reasons for this related to what I've just been talking about. One common theme is that early decisions that you make and are actually forced to make huge differences to both performance and compatibility on the other side, right? You don't find out that your file format was a bad choice until you've written a substantial amount of data and can't keep up with it on your cluster. Similarly, you might think, oh, I can create this skeleton of my schema first, and then migrate up to a point where I'm storing all of the data that I need to. Well, that doesn't actually work because some file formats tell you they have timestamps, but they actually don't. So there are a ton of problems just with choosing that one thing. Then all of these components and formats work slightly differently. The semantics were decided, by whoever implemented that format. Table support, I've harped on this already, is done manually for most projects that are accessing data directly through Spark or MR. And this is slowly improving. Parquet support through Spark SQL has support for partitioning, but again, going back to the problem of it works slightly differently than anything else. And you're still saying, I want this year, this month, this day, oh, and I want a particular range of timestamps. When we should be able to take your timestamps and figure out what day that's in. Another one that you probably don't realize is SQL engines can't trust the files that are in the tables because users can just drop random data in there. So all of the queries have to have what data you want in terms of the actual logical data, and you're responsible for selecting the partitions. Well, we can do better, and this is a list of things I think will fix the problem. I honestly just wrote some random stuff on paper, so here we go. We'll see if it actually does. First of all, right, one of the problems is we have this gigantic mess with no standards. We allow anyone to write anything, and then we call that an SQL table. Well, that's kind of a problem. If we want things to work together, we need to decide how we're going to do something and write our applications to that spec or that standard, right? Basically, all I'm saying here is write everything the same way, right? Choose some formats that are going to work well, and let's build out support for everything that we need on top of that in a way that's going to work no matter what SQL engine you're using, or if you want to process your data in Spark or MR. We need to implement this table-level view or abstraction pretty much everywhere and get rid of the file-level view, right? It makes no sense to have one application viewing this as a table and the other having to lunge paths and do all sorts of crazy things. Then we need to do things like build partition handling that actually handles partitions. Instead of letting you provide values in your Hive queries for both inserts and selects, what we want is for you to be able to say, this is how I want my data laid out. The records are automatically put into that structure, and we automatically figure out which files need to be queried when we're reading data in. And lastly, we have some engineering concerns based around this. We want to take and build essentially a standard API so that when we realize we would like to do something else, like improve the table format, we can have all of the applications using that API update to it without changing the applications themselves, without changing the tiny bits of logic that say how to get data to my MR job or something else. And this is really crucial if we want applications to be able to work across the stack, because there are so many pieces that have to work together. You've got your ETL pipeline that takes data from Flume, puts it somewhere so Hive can transform it. Hive puts it in a new place so that, say, Impala can do low latency queries on it. We need all of those pieces to work together and really agree. So we want this standard API so we can change things underneath it, and we want a common set of tools, say a reference implementation, or simply collaborate and stop rebuilding the same things over and over. So these last two, a standard API so that storage can be versioned and evolved underneath, and a common set of tools is pretty much what Kite is. It's a table-level API that you can use in MR, Spark, what have you. It allows you to depend on that API and not necessarily the underlying engine, not necessarily the fact that it's an HBase or HDFS, and we can also change that, right? If Kite implements a new table format, you don't have to care, right? We don't have to update every single application that accesses that data. We can update Kite and say, all right, if you don't know how to read this table format, use something like Kite. All right. And it's also a common set of tools. I'll demo the command line interface later, which is basically everything that you would expect. I can cat a table, even though I'm not going through Hive and things like that. So Kite defines as its core, so that we have this table-level API, a dataset level abstraction. So tables are datasets. You may have heard this term used in other places for basically the same thing, but a little differently. Yeah, all the CAS guys are smiling at me. So datasets are the basic building block. That's essentially a Hive table, think of it. They're identified by URI, and we have configuration that tells them how to behave. This is an Avro schema because it's fairly well built out, has concepts like nullability, times, dates, etc., and a partition configuration so that Kite can manage your data rather than forcing you to. It's compatible with Hive and Impala, and it provides that table-level view so you can select data using an API, pass that to an MR input format, and get just the data that you selected with predicates when you're using Spark or MR. All right, well, we kind of have to address this. Since we're in the CASC offices, how are Kite and Cask different? Well, Kite is an API that defines this dataset interface, and Cask does pretty much exactly the same thing. It has a dataset interface. Well, Kite is focused downward, down the stack. We want to provide some API that you can build on top of so that you don't have to care what's underneath your application. You don't have to care about those mundane details of how I decided to map your data into files. We care about serialization. We have an Avro-based API, so if you're using objects and we give you an in-memory representation, that's Avro. We provide compatibility, so we know that when we deliver a time type, you can use that across the ecosystem because it's defined in the upstream projects. Right? Avro and Parquet have defined how time should be stored, and we've done some due diligence to make sure Hive supports it, and Impala supports it, and a number of things. Scoop supports it, for example. So Kite is really focused on storing data right, so we can build out this pretty wonderful database and do amazing things without all these compatibility or application level problems. Cask is actually focused upward from that level. Cask has to store data somewhere, so they do, right? And they do a good job of it too. In fact, there are some similarities between Kite and Cask, but Cask is really focused on these higher level data set abstractions. So you can do higher order things like OLAP cubes and stuff like that. Yes, there's some overlap, but there's actually not too much. And the mission of Cask and the mission of Kite are actually quite distinct. All right. Things that we're currently doing, like I said, I think I've mentioned these, they're on my mind. Date time and timestamp standardization across Avro and Parquet. We're actually going to these upstream communities, because I'm sort of already participating, and saying, hey, let's figure out how we should store these times and timestamps and things for this format. What makes sense for the underlying serialization, and in the case of Parquet, what makes sense for us to use in a columnar store. We did this for decimal as well, and that's how decimal support was rolled out across Impala and Hive. And we're really concerned with storing data the right way so that it's going to be useful 20 years from now. We're also working on something I'm pretty excited about, a new table format with snapshot isolation. Because we don't want to have to lock, in order to have these low latency queries, access their data. And we also don't want to provide a completely unsafe database experience. So that requires a new table format. In order to move to that table format, we actually want people to just move to an API so we can improve it and evolve what goes on at the storage layer in the future. We're also working on an H-based encoding specification, exactly the same thing as our efforts for date, time, and timestamp, only a little more broad, because this is something where everyone writes data however they feel like in H-base, and there are some best practices that are being ignored, or just differences of opinion, and we want to standardize how that happens so that Phoenix can write data that Impala can read, and Cask can read and write that same table. And with that, I think that's basically what Kite is. Any questions before we move on to a quick command line demo?
Do we have a metadata repository concept?
Okay, the question was, do we have the concept of a metadata repository? So currently we use whatever one you want. So we have an API with which we wrap existing metadata repositories. And we have an implementation for storing metadata in a file system, so you don't have to have a metastore running. We can contact the Hive metastore and store all of your data there as a single source of truth. And we can also store some metadata in HBase if you prefer that. We think this is a fairly future-proof solution because the idea is to use whatever is established as the metadata storage for a Hadoop cluster. Whether that's the metastore or the next version of the metastore or something entirely new. Any other questions?
Do you guys support the schema evolution if you do it Afro? I think it support read and write schema evolution for different schema schema? Does Kite provide the kind of identifier to move different view schema for Avro, for example?
Yes, exactly. So Avro actually, one of the reasons we chose that as our object model, sorry, I'll repeat the question. Do we have some notion of schema evolution within Kite? And the answer is yes. We chose Avro because it has a fairly robust way of describing your data, and it's very widely used on the platform. In addition, it has different object models if you want to use your own objects, generate objects from a schema, or use some generic objects. We adhere to pretty strict Avro schema evolution rules, so those are very well defined and work well. We actually have some additional rules, so we'll keep all of the previous schemas that you've ever used on a table.
Yeah, transforming, okay.
And we'll verify that you can read data written with any version of the schema that's ever been on that table. And keeping an overall schema for this, even if you're writing out of MapReduce and you're writing into multiple directories for MapReduce, is actually one of the primary ways that we're making it safe and easier to use. Just no amp?
You sound much better without it.
I've heard that I'm fairly loud. Okay.
How does it relate to H catalog?
How does it relate to H catalog? That's a great question. So H catalog is a very similar thing in that I want all of the stuff that Hive does to be done when I'm writing from a pig job or a MapReduce pipeline. The problem with that is H catalog goes on top of Hive. So number one, it's not prescriptive with the choices you make, right? It's not doing the very first thing that I said, which is let's pick some standardizations for how we're going to store data and implement that across the platform. It says anything Hive can read or write, I can read or write, which is really nice, but you pay the performance cost and you pay the compatibility cost, right? So what Kite actually does is we've adopted the de facto standard table layout, and we're working with well-defined formats that we're confident we can deliver type support or improvements to across the board. So right now that's Avro and Parquet, because those are the formats that we as Cloudera like. I think we'll probably support Orc at some point, because I think this should be something that we use as a community project to improve the standard of storage on Hadoop. And for that, a lot of people use Orc. I just would have a hard time selling that to my management. I mean, yeah.
Does it provide JDBC or BBC connection, or is it kind of below?
So it actually, it doesn't provide JDBC or ODBC directly, because for that you want to use an SQL layer. So what we want to do is define a storage layer and APIs for making sure we all have the same view of that storage layer. That's what Kite primarily is. The Kite project is that view of the storage layer for programs that you write yourself. But we also have an influence on table format and standards that we make sure get implemented by the people with JDBC connectors. So you should be able to go and read a Kite dataset from Impala or Hive without any problems, because we've done that legwork to make sure we're writing everything in a compatible way. Right? So we want you to be able to choose your own JDBC connector, because we can all agree on the way things are stored.
Is there any similarity between this and how far M7 and M7?
I'm not familiar with that project.
Structures into the file system. You haven't heard about it?
No, unfortunately. I'll have to reach out to them about that. Yes?
It seems like if you're at the API level, you need to include Orc and other projects in order to make sure the API is agnostic.
So I think it is, that's a good point. And what we actually have been doing is going more in that direction, more drastic. So we're looking at, if we had a stream, for example. What would a Kafka-backed stream do to this API? Or we actually have HBase support that uses an Avro-based encoding, and we have HDFS. So how do we reconcile the differences between those APIs, but still have common methods for the things that you want to do that are invoked? So, for example, stream-based reading and writing can be implemented across both. And I think that's actually more important than the file formats, because the file formats essentially give you the same record-oriented view of the data.
Yeah.
When you decide for this architectural decision, like when you decided for the file-based API, for the table-based API, right? Did you look at the impact it has on other factors? Like for example, if you interact with Kafka, right? It can impact the throughput, right? Because you have all this stuff going through the tables, right? So everything has to go through that. And how is that?
I'm not sure I understand the question.
So when like if you do a table-based API, right? I assume you have some kind of an intermediate
Yeah.
serialization for the tables, right? So then that's going to be a huge limiting factor when you interact with things like high throughput. Kafka,
Yeah. So we've actually discussed how we would do a Kafka-backed API. And right now the API has this concept of views, which is kind of like a database view, where you give it constraints. And actually, this is how we do projection as well. So you can give it a schema, and we'll project just those columns that are present in the schema that you want to read with. You say, I want these columns by expressing a schema. Or saying, this is the object I'm interested in, we'll grab a schema from that object and use that as the read schema. In that case, we have this ability to say, this is how I want to view the data. This is how I want to work with it. I don't want to see things where there's a null in this field, or I'm only interested in timestamps from A to B. Now, I think this could be extended to Kafka as well, although we have not done the work to make that happen, but that's the approach that we've been discussing.
Well, that's the easy part, like the read part, but how about the write part? Like when you have data coming in, the write throughput, I think, is going to be much slower, right?
Possibly. It depends on how you're partitioning, right? If you're randomly partitioning to go into these Kafka streams, then you should just be able to parallelize that, right? Because you don't have, you should have very little contention for getting the next record in. I think so. Don't quote me on that. All right. Yeah.
Well, the other thing is, if you sort of step out a few years from now, I mean, a lot of data can be stored in all this very expansive memory. And disks are becoming some kind of memory. So it's going to be a different way of access. It's going to be cache oriented. How do you stage things up to the CPU? So
Yeah. So there are two contributions that Kite makes. And I think number one, and the one that I'm really concerned with here, is the standardization of storage. Let's figure out how we're going to do it. Everyone implement the same thing, so things just work together. The other is, perhaps Kite won't be the API that you use for that. But I think we have to preserve those same ideas of, let's think it through, let's come up with a good API, and let's try and have some layer between the application and storage so that we can evolve and change the storage underneath. Cool. Should we get to a quick demo?
Yeah.
So, I have the demo up here. All right, so just as a warning, this is a demo. I usually play the demo drinking game, but I didn't bring a beer. So anytime I screw up, I drink. I appreciate it if you guys do the same. Sorry, anytime I get something right, you drink. Which I guess. To be fair. All right, so Kite has this CLI. You can actually download it. It's an executable jar. Put it on a Hadoop cluster, and it tries to find where your Hadoop stuff is and go do it. Figure out all of that stuff. It's about 12 megabytes. So I have a local copy here that, to be perfectly honest, I compiled myself, so might not work so right. So Kite dataset is what we're calling it. And we've actually got all these commands. You can create a data set, create something empty. You can actually create a data set from data, which is what I'm interested in doing right now. You can copy data from a data set to another. You can compact it, whatever, right? And the important thing here is all of these work through the exact same API using whatever storage you've configured underneath. Whether that's write everything into year, month, day based on my timestamp field, or whether that is write all of my records into Parquet. Right? We give you the exact same object model, no matter what your data records look like or what format you're going to. So that's actually really cool. One thing I would like to point out that we just released in the 1.1 release is this compact command. So if anyone has had problems where they've run into way too many tiny files in a directory, Kite can actually take care of that problem and replace those in place by copying the data out into larger files and then doing very few operations to move it back in by swapping out the directories. So that's actually a really cool thing, although because we don't have a table format to support it, it's currently unsafe, so you need to schedule a maintenance window. So what I'd like to demo for you today is I've put some data just in S3. So I've got this bucket called Kite Data Test. I'll make this bigger. And I have the Movie Lens Movies data set, which is commonly used. Is that minutes or seconds? Minutes. The Movie Lens data set, which is commonly used for like machine learning. You can build a recommender system based on it. I've transformed that into JSON, and I've put it in this Movie Lens/Movies folder in S3. Now, I'll come back up here, I have my Kite dataset command. And because I don't want to screw this up, I have things that I've already done. All right, so I'm going to create, it's supposed to be S3. I'm going to create a data set just around that file. So create data set, this is the URI. Hopefully you guys can see that. Data sets are all identified by URI. It starts with data set, and then it says where that data set is stored. This one actually is going to be stored in S3, so I use the S3A URI. Then, because it's a URI, I'm just going to pass my credentials here, which I hopefully won't display to an entire room full of people. And I say the host is my bucket name, and I'm going to be using the path /movielens/movies. So run that. Of course, what this is doing is it's going out to S3, grabbing that file, inferring a schema from the JSON records in that file. So it looks at the first 20 or so records, figures out what the schema is, and then gives me an Avro schema for that. Then it says, well, what does the partitioning look like? It's just a file in a directory, so it's not going to be partitioned, and it'll give me this data set that is that can be read using a particular schema that is not partitioned. So let's take a look at that schema. Dataset S3A, blah, blah, blah. And this is the schema that I inferred from that data. It's an Avro schema, typical schema evolution rules apply, so I can actually output that to schema.absc. Wasn't planning on doing this, so I might be drinking. Then schema.absc. All right, I'm going to say that video release date is either a null or a string. And, all right. I'm going to use my update command. Give it the same file that I've now modified. This is going to go update that schema. And although I didn't choose something that would fail, it runs it against all of the previous schemas so we can see what's going on. Well, let's refresh this view of the data. Because I don't have a Hive metastore, I've dropped a metadata folder here. and I have a schemas folder where I said we store all of the previous schemas. And now we have a 2.avsc, and if I were to access that, you'll see that I've, of course, changed it, which is neat. So now we have a nullable string, which is what I changed in that file. Now, actually, I'm going to just cat some records. So show things in that data set, which is what I intended to do. Great. So we can see movies that are coming up and their IMDb URLs. And I'm going to just quickly, as the last thing, remove that and show you that it fails, which is intended, so I don't have to drink. Now, I've removed the fact that it's nullable, but I may have written something with nulls in it. So it's actually an invalid migration to say I could go from something that might have nulls to something that definitely doesn't. So what I get instead is, it's kind of hard to read, is this error message that says schema can't be read using the existing schema. So, schema cannot read data written using the existing schema, which says, and here are two schemas, they're incompatible. I think I'm probably running out of time, so I'll open it up for last questions and they'll shut me down when it's time. Anyone? All right, well, thank you all for listening to me. I really appreciate you coming. I'm Ryan Blue at Cloudera if you have any questions. We really want this to be something where we can collaborate with other people, other companies. Like I said, the whole idea is to improve the state of storage. Thank you very much.